Right, well, contrary to what it actually says on the original agenda, I'm not Steve Brown. My colleague was not available, so in his place I'll be presenting this. For my sins, I initially was a process engineer for bareboard manufacture and then assembly for ICL, who at the time were the UK's indigenous mainframe manufacturer. Then that moved into contract manufacturer, and then when that finally disappeared, I joined what was then Cookson, Alpha Fry, any one of a myriad of names, but really Alpha as it is now. Okay, so this conference is really around tomorrow's solders, and that made me think, well, Innolot, an automotive high reliability alloy, is that the right name for it? I know when Hector was here before we were discussing it, maybe it should be described as Innolot, the forgotten alloy, or Innolot, an alloy whose time has come, because it may be tomorrow's solder, but you know, it's been around a little while now. So what we're going to talk about, I'm going to talk about background to the project, and now the data I'm presenting here really comes from the original consortium and working group, and it's all their hard work. I am really just the messenger coming out and telling the story again. Okay. It was a consortium-based development approach. That consortium worked on defining an alloy requirement and then went away and developed that alloy. So it started with an end use, worked backwards. It wasn't a case of somebody came up with an alloy and then tried to find a use for it. We'll look at the methods that chose to strengthen the alloy, the alloying elements, defining the alloy composition, at which point it reminds me that they always say with comedians, never be the last act on, and practically everything I'm going to put, whether it be the cerium question, is, you know, those sort of things come up. So there's lots of things other people have spoken about will be repeated. We're going to look at the creep performance of the alloy and compare it to existing alloys, its microstructure, its process performance, because ultimately we want an alloy that is usable. Initially this project was for paste-related applications only, although it has migrated over the years. Ultimately, it's thermal cycling performance and something about vibration. Right, so the project background, as I said, it's not a brand new alloy. It started in about 2000. Publication of the final results was about 2004. But in 2000, some people within the automotive industry realized that electronics modules were going to be pushed closer and closer to the area of use, reducing the amount of wiring, and that would mean a harsher environment with higher temperature and higher vibration levels. And if we go back to 2000, I mean, in the automotive industry, there were two alloys. You either had it with silver or without silver, 6337 or 62362. Great alloy, it's been there for years, but it contained lead. That was obviously, it's going to be its nemesis. And it didn't meet the requirement for higher temperature applications. Then, in terms of lead-free, there was the copper-free version, the 96.5, 3.5. There was the tin copper and also the modified eutectics based around there with an extra element. They had high processing temperatures, but their reliability potentially was limited. And then in the more commercial electronics sector, where the move was towards the standard SAC alloys, whether by 305, 405, 387, 396, think of a number somewhere between. Okay. So as I said, this was a consortium-based approach. It had end users, it had leader, it had academic partners, and then it had suppliers between suppliers of equipment, components, and also alloy suppliers. I did intend to put a pun here. The strength in this alloy, every pun intended, really is the consortium approach. That it's not a one person supplies it. There was a need and people working on it. They were the suppliers. Initially, it was Stanol, and then once the project was finished commercially, that moved over to Heraeus, who are now one of the three people supplying the alloy. Okay. So I said we're going to look at alloy requirements. Well, the main thing was it had to be lead-free. The second thing was harsh environments. Now, depends on the publication. Sometimes you'll see the figure 150 centigrade, sometimes 160. I'm not going to argue over 10 degrees really here, but typically pushing it up to 150, and we will look at what the limitations of the benchmark alloys were considered to be. Survive 1,000 cycles of minus 55 plus 150 thermal cycling. Again, I've seen published figures saying 2,000, but the thing is to take it as far as you could. Try and get a reflow temperature, ideally less than 230. Acceptable base material costs. There's no use producing an alloy and then using those wonderful alloying elements, costalotium or unobtainium, which do tend to occur. It's great, but people have to use these in volume, and therefore it's got to be cost effective. And acceptable toxicity considerations. So really, the project definition was how to improve the creep performance. Obviously, the thermomechanical failure being a creep fatigue interaction, but the creep part of it being considered to be the greater content. So there was requirement to increase creep resistance, and what they did was they took a base alloy, in this case the standard SAC 387, considered to be the eutectic, or depending on who you talk to, considered to be the eutectic alloy. So what they looked at improving creep resistance, and how they did that, they looked at solid solution strengthening. So in this case, putting elements in that either had larger or smaller atoms that inserted themselves into the atomic or lattice structure, and in effect bent that structure, for want of a better expression, and then dispersion hardening, so where you were actually precipitating phases or materials out. But both methods really were there to stop dislocation movement and therefore creep mechanism. There's plenty of papers, and I'm sure Sophie will cover a lot of this later. They're a far more knowledgeable mechanical metallurgist than myself. So to do that, we needed to look at some alloying elements. And we did consider health and safety, and we did consider environmental impact. So that was the consensus opinion. And they were the elements that we had to look at. There were some non-suitable alloying elements, and as we said, cerium is in there. They were considered amongst the group just not to be the right materials. Some were pushed out the project on the basis of cost. The indium is great. It's a fantastic element for increasing wetting. It produces some great ternary and quaternary alloys, but it's just too expensive for what they were trying to do. So they were the alloys that we considered not to use, and that really left us with a lot of the common elements that have been used in solder alloys over the years, either as binary or even ternary systems. So bismuth, it gives us a solid solution hardening. We know it lowers melting temperature, two of the things we wanted to do. The nickel, we knew it could give us dispersion hardening. And then the antimony, again, solid solution hardening, but the thing it did here that we didn't want is actually raise the melting temperature. Okay. So how were we going to choose how much and which of these we were going to add? So if we look first here at the creep characteristics, so this is just a SAC alloy, the base SAC alloy, and then we added each one of the elements the working group did that. And we looked at the creep stress, and as you can see, the solid solution strengthening is improving the performance with bismuth and with antimony, and in this case the nickel is actually slightly reduced. Now I'm guessing that's because it mops up some of the, there's not enough copper in there, it mops it up, it's possible, I'm not sure of the mechanism, but that's what we had. So we had single element additions to make ourselves a quaternary alloy. The whole idea of this was to design an alloy with a maximum operating temperature, which had been targeted at being 150. So if we look now at the creep resistance, here we've got the figures for the tin lead alloy, and data that the end users had, they were quite happy with the tin lead performance at 80 centigrade. They would get a typical similar performance from the SAC alloys up to about 115, 120, somewhere around about there. So the idea was to get the same creep performance out of the 6-part alloy at an operating temperature of 150. Now, using that technique, what it allowed them to do was the two things we were chasing was operating temperature and creep resistance. That creep resistance obviously coming from here. And what we were trying to do is get ourselves an alloy that would use those elements but would work up in that target quadrant. So we looked at the single element additions. First of all, we've got our tin lead benchmark down here. We've got our SAC 387 benchmark. So we add ourselves some antimony. Great, it increases the strength, but unfortunately it increases the temperature. The nickel, as we've said before, it actually reduces the strength. And the bismuth reduces the soldering temperature, increases the strength. So it came out that we couldn't just buy the group couldn't buy a one element addition, make a quaternary alloy that would fit the bill. So what they did was they looked at adding multitude and came up with a 6-part alloy, which is quite a complex alloy, I guess, for a solder. And by making additions, which you will see, there's a lot of work behind this, how much they added, but to take us into this region, and they came up with a final Innolot composition of the 387 base alloy, 3% bismuth, 1.4 antimony, 0.15 nickel. Okay. Having made that alloy, what's its creep performance like? Well, here's two creep strength plots, one at the ambient temperature and one at the operational temperature. And as we can see, there is definitely a performance increase. So mechanically, we've ticked one box. We've got something that's stronger. Doesn't necessarily mean it's usable yet. So having come up with an alloy composition, can we use it? Also, here is a far more, this is 100 degrees centigrade, there's a creep rupture test, but it's really saying the same story. It's a little less subtle than the other tests, but again, it's showing you there is a difference, depending on the creep stress that's applied, then it is, it does show a difference. That was against the 305 alloy, by the way. Okay, so we've done this, we've made our alloy, what have we done to the microstructure? And again, as I said before, don't be last up because, you've all seen this before. So, nice tin matrix, tin silver intermetallic compound, and copper tin intermetallic compound. Having made it a 6-part alloy, this is what we've done to it, or this is what the consortia did to it. Right? They basically, you've got your tin matrix now with your antimony and bismuth solid solution strengthening. You've still got your tin silver intermetallic compound, but you've now got the copper nickel tin intermetallic compounds in there, giving you your dispersion hardening. We've got an alloy. What do we know about it in terms of wetting performance? One of the things, the targets, was to get an alloy that you could use at a lower temperature. And with the DSC plots, you can see that the solidus has shifted by about 8 degrees. It's interesting that, how many thermodynamicists does it take to agree on a melting point? I think most of the people who supply the alloy say the melting range is around about that at the moment. So taken to be somewhere about 206. So, depending on the heating rate, etc., there's a little bit of a shift, but there you go. Okay. So we've added these elements. What's it done to make the thing usable? As I say, in terms of wetting, bismuth enhances the wetting, antimony reduces it. So some tests were done, wetting balance tests on copper OSP. It was done on multiple materials. We tend to do a lot of our screening tests on copper OSP materials, especially from a solderability point of view, because normally that is the hardest to solder. It's often a starting point. It was tested on different atmospheres with a constant flux type. So really what we were looking at is varying the temperature on a solderable finish, with the specific aim is to see how low we could make it wet, and was it wettable at a lower temperature than the standard SAC alloy. And as you were trying to explain before, that this point, this time to buoyancy, this neutral line, when you first put this is shown putting a piece of metal, whether it be a wire, a piece of laminate, into a liquid bath, but these tests often use globules and surface mount type configurations. But it's the same thing, when you first put it in, it's cold, the thing is buoyant. gradually it'll start to the heat, it'll start to wet out, and you reach a point here, C, which we can measure this at time to zero wetting force. Sometimes when people do, they'll do these to time to 2/3 of the maximum wetting force. They tend to give you fairly similar results, and then we've got the maximum wetting force there. So tabulated, not particularly easy to see, not particularly easy to look at. The most important thing is in graphical form, the temperatures. That's what we're looking at, the wetting results. So 225 compared to 235. So the SAC alloys, you can see at 225, they take a long time to wet. I mean, the degree of superheat over the melting point, it's not that great really. So the Innolot does show the potential to wet at that temperature and the same and have a wetting force. So that's doing it from a wetting balance test point of view. As a paste, we will often do things like we have a paste wetting test where we print tram lines with different spaces. So there'll be 2 tram lines on each of these, and then with varying distances, and you look how they join together. That's another numeric way of doing it. We tested that, and we found how it performed on each of the different finishes. But really, there is no substitute for the real world, and this wasn't part of the original test, but this is a great assembly because this particular assembly is on an aluminium-backed PCB, and it has a massive delta T. So this happens to be a big surface mount transformer, and here you've got some small QFN, an SO device, and these will be typically 240. I happen to know that part is reflowing at 229 centigrade, and they're producing the product day in, day out. It will reflow at 229. I am going to mention a little bit about the lowest temperature again in a minute. Okay, so we've got an alloy. We've done something to make it mechanically stronger. It looks as though we can use it from a applications point of view, from wetting. Has it achieved the final target, and that is, has it strengthened the alloy in terms of thermal cycling? So here we have the base alloy, the Innolot, here, the SAC alloy there, -40 to 150 thermal cycling in groups of 250 cycles. This is on resistor and capacitor components, so there's no compliant leads. The components that, in this particular case, tended to show first failures in the end user environment, and we can see a clear shift in that the Innolot are not showing the initial failures anywhere near as soon as the standard SAC alloy. Okay. A measure of shear testing of capacitor components again after thermal cycling, and the reason people are doing this is because obviously you do get some degree of joint damage, and it's trying to really assess how much of the joint integrity has been lost, how much is left after it's been shake, rattle, rolled, or thermally cycled in this case. And here we've got 2 sets. That's -40, 125, 1,000 cycles, -40, 125, 2,000 cycles, and -40, 150, 1,000 cycles, i.e. the target condition. And then the residual force to shear tests, to shear the components off. And there is, whether its amount of residual joint or the inherent increase in shear strength of the alloy, I'm sure it's a bit of both, but the Innolot has, or does show, a higher residual strength. And testing again now after thermal cycling, but at elevated temperatures, and you can see that the Innolot clearly outperforms others. Now, one interesting thing here I don't know the answer to is that it's interesting, you do notice that the Innolot appears, and it's only a small sample here, appears to actually get stronger, then drop down. Now, whether or not this is some of the aging type phenomenon that we've heard, and that is, maybe almost certainly it will be, because if you look at other solid solution strength and also precipitation hardened materials, I mean, there's a lot of age hardening goes on there, so it may well be that there is some growth of the particles. Okay. And then finally vibration testing, and we had a discussion earlier on about whether the vibration test is done here as a thermal cycling and then vibration, or done at the same time. But this is just a snapshot of the data. We're basically finding that both the force and the time, the duration of the vibration for the sac is a lot less than with Innolot. It does seem to meet the requirements that were set of it. Okay. So in summary, in the original work, Innolot alloy has been proven to be mechanically superior to 387 in vibration and with or without superimposed thermal cycles. In thermal cycling, it has definitely been proven both in the laboratory and, as I see, end users adopt it. I mean, there are really two forms of end users. There are those that were originally in the consortia who developed it for their own use, and there are now what I'm seeing are what I call late adopters that have found potentially they're reaching a limitation in SAC 387 in an assembly. And I mean, a lot of these people will do things like if they have a problematic component with, we were talking about moulding compounds, or maybe a type 1 T-SOP, so type 1 T-SOP's off the use list, a particular size of large ceramic component. They've done all of that. Now they need to get an assembly which has got the already approved group of components. And what you're finding is that the reason this is happening is that, especially in the automotive industry, the test requirements are getting tougher and tougher as warranty periods are going up and up. The end purchasers of the assembly from the OEMs in the automotive industry who may make engine management systems or braking systems. At one time it was a 500 cycle. Now it's 1,000 cycles. Now it's 1,500 cycles. Now there's still the argument whether these test regimes bear any relation to final life, but people are saying you've got to test it more aggressively and longer, and 387 or 305 is running out of steam. It's a good fit for harsh environments, so we see it in this area, and we have seen it in lighting, specifically management of high-intensity discharge, some applications there, and for some LED. This tends to not be the daytime running, but the high power, high heat dissipation. Okay, it has a melting range from 206 to 218. Right, reflow recommendations. If I was starting, I'd always say 230. You can push it lower, but you've really got to do a lot of due diligence. I'm very comfortable with the 230. That can be done, but you're pushing the degree of superheat you have at a melting point. It's quite a low margin. It's available in paste, preform, bar, solid wire, cord wire. Certainly the wire is an interesting case, that they made an alloy and then they wanted a wire, and everything they did to the alloy to make it creep resistant made it wire manufacturing resistant. So the partners who are in, the manufacturer partners have had to find go to extrusion-based techniques, and it's available currently from 3 suppliers, of which we are one. So the good thing is that if you like the alloy but don't like a company, or you don't want a single source, then there is an option not to single source. And just one last thing is that really goes with Dominic's roadmap. I mean, we do see potentially in the automotive sector that the usage of SAC alloy will shrink. There'll be some low silver and low temperature for certain more benign applications, but we do see that potentially this alloy and any other alloys that are introduced that do similar things will be growing, because it's only going to get more and more, the environments are going to get more and more harsh. That's it.
That's great.
Okay.
So I happen to know already that there are questions on your paper.
Oh, good.
So, Farrell first.
Yes, since you add elements to increase precipitation and solid solution hardening, you might increase the risk for brittle fractures in the intermetallic layers. Is that something that you have investigation?
I thought this was coming after I watched your I'm sure there is data out there. For instance, I know that one of the questions we spoke about is BGAs and transitioning the spheres to Innolot spheres. Did you ever get any Innolot spheres? Sophie has had some Innolot spheres. They can be made, and part of the component people will be probably doing high-speed shear tests on them. I've not seen the results. They probably do exist. I can't answer the question. I probably know a man who can, but there is always that risk that you've put a lot of nickel in there, for instance, and some of the mechanisms you've seen could or could not happen.
Thank you. Dom, another question over there.
There was a study of an American aeronautic company about the risk of antimony leading to whiskers. Did you study this risk of having antimony in the solder and leading to whiskers?
I'm not sure if the original consortium did. I don't know if they've done a whisker study. We have not done any further whisker studies on antimony additions. Mm-hmm. No.
And there's a more general point there about the use of antimony generally in alloys.
Yeah.
Do you have any sort of comment on that? Have you seen any kind of kickback on the fact that you have chosen to use antimony here?
Well, I mean, if we go back to the original choice list, that was one of the hot favourites to be taken off the list at one point. Again, at the moment it's there. If it does eventually disappear, then there might be a sudden hurry to engineer a 5-part alloy. There was a lot of work done in between with 5-part alloys, which have some results, but they went forward with this alloy. If antimony was to be excluded, then it probably would have to be a relook at that. I mean, I don't know what the current. Well, the two guys have gone now. I don't know what the current status is on antimony as a material for soldering or putting in soldering alloys.
Anyone got any comments on that?
The guys were saying this morning there is no risk from antimony, and everybody says that I've asked there is no risk from antimony actually being banned in the near future. Right.
So at the moment, no.
Any other questions on the Innolot paper?
I'm going to be fit.
One on my right here.
Sorry, Bob Willis has just asked, what experience has been seen with continued operation at 140 to 160 degrees C?
I mean, the alloy is designed to be used continuously at those temperatures. Over there, yep, as at those temperatures, and I think Bob and I actually discussed this yesterday, but I've not seen any data from the, what's the maximum you can push it to in terms of hours? Because, I mean, one of the things is how does this microstructure age at continual high temperature usage? So there are quite a few unknowns still.
There are. I mean, I was going to ask you actually, Alan, are we talking here about what we might call a nanocomposite alloy? You mentioned dispersion hardening at some point. It's not just strictly dopant addition. Am I right here?
No, these are quite reasonable additions. These are,
Yeah, so have we actually got particulates into metallics? Is it the microstructure is more than just a...
I think Sophie's got some electron micrographs which will give you a bit more detail than the conventional microsections there. But yes, there are significantly... well, I think you'll see how it affects your nano indentation. So I think you're going to get some of the answers to that in a paper in not too great a time.
Okay, good. Any other questions over there?
Blimey.
Just say who you are would be helpful.
Hi, Gavin Jackson, Henkel. I'm just really interested in your thoughts of this alloy was available in 2000. It's got quite a lot of, I'd say, trustworthy reliability data because it was put together by a consortium. So I'm just interested in your thoughts of why in 2013 is it Is it becoming more popular, or what were the barriers that perhaps people were struggling in the mid 2000s?
As I said, one of the titles potentially to use was an alloy that the time has come. I think there were lots of reasons. One, many end users didn't need it. It was in the ammunition locker, but they just didn't need it. Two, if you weren't going to those temperatures, you probably wouldn't see any difference between a standard SAC alloy. So for many people, its properties were wasted. Three, it was designed as a paste-based alloy, but subsequently people have learned to use it for selective soldering. Wires have become available. So there are other methods of using it. So that's happened. There's always the risk of being the earlier adopter, that you don't want to be the earlier adopter of anything. So I think it might be a wait and see. So with the original consortium, as you probably know, that those people who worked towards its development, some of them became quite big users of it and have been. And really what I'm finding now is it's that people are finding the standard SAC alloys are potentially running out of steam. I say that doesn't mean that there won't be another alloy that's a 4-part alloy from another person that may meet the requirements. But they are now, it's a case of, well, what's available? And commercially, what is available? There are a few alloys, but it's possibly one of the potentially best. I'm sure there will be, whether it be a particular vibration environment, whether it be a particular set of operational parameters. I'm sure there isn't the perfect alloy. I mean, what isn't perfect about it? It's got 3.8% silver. So the first thing people says, well, how much? Get rid of the silver and it'd be a bit, it'd be less costly. So it's there is no perfect alloy, but it is, I think, is an alloy that has some potential for some of the applications out there now that have arisen.
Yeah, thanks. Now I think it's an interesting point about the silver, because with Wayne's talk there, that kind of goes the other way. I think one of the things that's interesting as well is perhaps in the early 2000s there was still quite a lot of mixed technologies. So
that's a very good point. That is on my presentation. Do not have any lead on your component. That is a glaring omission on my behalf. If you have any lead, you do form a low melting point phase, I think about 98 centigrade, and your assembly will well and truly fall apart.
So now we're into more complete lead-free systems, where the risk of lead contamination is a lot lower. Then perhaps that's why there's maybe more uptake for this alloy. One of the reasons, not the reason, just one of them. And
also its market segment that developed it, Automotive, did then develop it and then said, well, we're not going to change from tin lead. So many people just sat back until they ran out of runway, and then now it's a case. So I think there's a combination of quite a few factors as why the uptake hasn't been so great, and now it's time to blow the dust off it perhaps and look at its potential in other environments.
I agree. Thank you.
To have this high reliability at these high temperatures, is it sufficient to have only the solder paste, which is Innolot, or you also need solder balls with the same composition?
They are solder baths. One of the questions from many people was if you were using selective soldering. I mean, we're happy with a SAC alloy of generally, you start, depending on what circuit assembly you were soldering, you'd start with SAC 305, and then you'd just use SAC 300 as a top-up alloy, and the choice of two alloys to maintain your process. The worry here was, well, what happens if the nickel level dropped? Would I end up with multiple top-up alloys? From what I'm seeing at the moment, it isn't as bad as first thought, but I think, well, I know that those people working with it, that's the sort of data that is quite closely guarded, really. But I think it's possible. In effect, you keep the same alloy structure. I mean, the limitations, the alloy constituency, the tolerances were set originally and are pretty well known, and it is possible to maintain a selective bath within that range. Selective baths often, unless where's Andy got me? You use very large baths for your chimney type systems. So it's not easy to say, well, if it goes a little bit out of kilter, we just change 10 kilos, whereas some of the smaller end selective baths, which are, say a single nozzle, maybe 20 kilos, and, you could just say, right, use it, and after, 3 or 4 weeks, you just change the alloy. There are ways of managing it. It is possible to do, and the tolerances are reasonably well known.
Any questions on that? Great, well, thank you, Alan, for that. You've got such a good grilling, and really well, and it's obviously a very interesting paper. Thank you very much.
Well, I'll say it's the work of a lot of people. It wasn't, not just one person.
That's right.